Hello and welcome to our next lecture. Today I want to briefly discuss how you can use the method of separation of variable on non-homogeneous equations. We're going to consider only the example of the heat equation, and the algorithm I'm going to discuss today can be easily extended on the case of the wave equation. The Laplace equation is a little bit different, so we're not going to talk about it at all. Let's consider a simple problem of a heat equation with an extra term. Non-homogeneous equations differ from the homogeneous counterparts by an inclusion of an extra term in the equation. In the particular case of the heat equation, this extra term adds a little bit of forcing on the time derivative of u. Previously, the time derivative of u was dependent on the second partial derivative of u in terms of x, and this modeled the process of a heat transfer through a thin insulated rod. However, if at different times and at different positions x, I'll pump extra heat into the rod, then I will cause a different rise or fall in the temperature. So here f, when positive, adds a little bit to the time derivative of u, increasing the heat a little bit faster than the rod would otherwise do if no external heating is applied. If f is negative, it has a cooling effect, either slowing down the rise of temperature or completely reversing it. I'm also considering the case when the temperature is kept at zero on the boundary. If the temperature at the boundary is kept non-zero, this method can be easily augmented with the trick I introduced earlier for non-zero boundaries in the case of the homogeneous equation. The big question is, how should we alter our method of separation of variables to accommodate for an extra term in the differential equation? And the answer is we use the previously derived results to guess the form of the solution, and thus deriving the solution for this particular problem. In the case of a homogeneous equation, the solution was always some kind of a sum. And in the case of the zero boundary conditions, it was always a sum in terms of n going from 1 to infinity. There was some kind of function of t times sine of pi n x over L. For the homogeneous equation, the function t was just an exponential function. But here I'm going to assume I don't know what this function t is, and I know it's going to be different for every n, so I'm just going to denote it as Tn of t. If the solution has this form, we would like to have the function f of xt expressed in the same form. So we're going to compute a series expansion for f of xt as well. Can this be done? Absolutely. If we consider function f as a function of x only with a parameter t, then for every fixed parameter t, this is just a function of x that should have its own sine series expansion with its own coefficients, cn or whatever we call them. But for different values of t, those coefficients will have different values. Therefore, the coefficients themselves will be functions of t. And we compute the coefficients just as we compute the coefficients in any other case. It's t over L, the integral from 0 to L, the function itself, times sine of pi n x over L dx. You can easily see when we integrate with respect to x, x will disappear and will produce a coefficient for every value of t. I know this is a little bit of unorthodox, but there is nothing wrong with thinking about having a series with coefficients that are dependent on t or z or whatever else your parameter is. So having these two expansions for u and f of t, we're going to plug them into the equation. So ut is just the time derivative of the series, and I'm going to assume that this time derivative is going to be the summation as n goes from 1 to infinity of t prime of t times sine of pi n x over L. uxx is going to be derived with respect to x, so it's going to be the sum as n goes from 1 to infinity of t times the second derivative of sine is negative pi n over L squared times sine of pi n x over L. Plugging this into differential equation gives us that the sum of t prime of t times sine of pi n x over L, as n goes from 1 to infinity, should be equal kappa times the sum of t times negative pi n over L squared sine of pi n x over L, plus the function f of xt, which is expressed as a sum as n goes from 1 to infinity of fn of t times sine of pi n x over L. You can see that every single sum has pi n over x over L in it as a component. So if I rearrange this, then this becomes a big sum as n goes from 1 to infinity of terms like t prime of t minus kappa times t of t times pi n over L squared minus fn of t. The whole thing is multiplied by sine of pi n x over L. And since I moved all of the summation terms to the left, on the right I have only 0. So it seems like I have a summation of sines that adds up to a 0 function. There's only one possibility for it to happen, is that every single coefficient for the sine function is 0. So in order for the sum to sum up to a 0 function, we have to have every single one of those things to be 0. So we have a differential equation for t. And this looks like a first order non-homogeneous equation, and we usually solve this one with the method of integrating factor. Second equation can be solved with a method like variation of parameters or undetermined coefficients. Depends on how complicated the function fn is. And the function fn of t is a known function because the function f of xt should be given to us in advance. Therefore, each fn can be computed. Every differential equation has to be supplied with an initial condition, and the equation for t is no exception. But how do we get such an initial condition? Well, we do know that for time t equals 0, the solution u of x 0 should be f of x. But at the same time, it is a summation as n goes from 1 to infinity of t of 0 times sine of pi n x over L. Therefore, each t of 0 has to be the sine series expansion of the little f of x. Now you might be a little bit confused about all of the sums that we're doing. So let me repeat again what we're doing and why. First, this was just an assumption that the solution u of xt has the series expansion. We knew this was the case in the past, but there was no ground to assume that this is going to be true in the case of a non-homogeneous equation. However, it did work out, but in order to compute the solution in the form of such series, we also need to express f of xt as the same kind of a series. And when we do so, the original differential equation breaks into infinitely many differential equations for Tn of t. I noticed that I forgot to put a subscript n on all t's, so I'm just going to quickly do that. So the first series expansion was just to obtain a differential equation for t. Now, once we obtain the differential equation for t, we need initial conditions. And the initial condition for a function u is prescribed by the function f of x. and the function f of x has its own series expansion. And it turns out that the series expansion coefficients Cn for the function f of x also play the same role as the initial conditions for the function t. Because initially the sine series that we have should add up to little f of x. So therefore, we've got ourselves the following algorithm. First, compute fn of t as the integrals Once you computed those fn of t, you can compute the solution to the differential equation for t. These are non-homogeneous equations, and sometimes solving non-homogeneous equations, even such simple one as the first order non-homogeneous equations, may be a little bit difficult. Each one of those equations has to be supplied with an initial condition, which we compute as a sine series coefficient to make up the function f of x at the initial time t equals 0. Once you produce those solutions, you just add up the building blocks and that will produce your final solution. Let's look at a very quick example. Here I have a thin rod of length 3. It has a heat conductivity constant kappa equals 1/2. Initially the rod was kept at a 0 temperature, and both ends of the rod are kept at 0 temperature at all times. At the time 0, I'm applying heat to the middle third of it for x from 1 to 2, and I do it for only 25 seconds, at which I turn off the heat. And once we solve the boundary value problem, we'll see the evolution of the temperature of the rod. Since it's a heat conduction problem, we have to start with the heat equation. Kappa is 1/2, and the function f is given to us as a heat only applied on the interval from 1 to 2. You can quickly recognize this function as a characteristic function for the interval from 1 to 2. H of x minus 1 only turns on at x equals 1, and h of x minus 2 turns everything off at x equals 2. However, this is in terms of x. In terms of time, I multiply by h of t, which starts applying heat at t equals 0, and then stops applying heat at t equals 25. The boundary conditions are u of 0t equals 0, and that equals u of 3t, because at both ends the temperature is kept at 0. And initially, at time t equals 0, my temperature was at 0. This makes this problem very easy to solve. Let's go ahead and do that. So here I define capital F of xt as the function that I just provided. This integral computes the sine series expansion of the function f of xt. You can quickly see that the function depends on t only, and the dependence on x has disappeared. As an experiment, let's plot the function f of xt for x between 0 and 3, and t from 0 to, say, 50. So this is what's going on with my heater. It turns on at time equals 0, and it only heats up the middle section of the rod, and then it turns off at 25 seconds. Just out of curiosity, we can add up the Fourier series expansion. I'm going to copy the expression obtained for the sine series expansion. I'm going to give them name fn of t. And just out of curiosity, we can compute the summation of the sine series expansion of f of t and see what would be the graph of it. Looks like 10 terms are not nearly enough, so let's add up 40 terms, plot them. You can see there's a little bit of a cutoff due to the Gibbs phenomenon going outside of the box, but you can see we're getting pretty close. So this series expansion does represent this function more or less accurately. Then what I need to do is I need to solve the differential equation, and since initially the temperature was kept at 0, the sine series expansion of the function little f of x, which is 0, is going to be 0 for every k or every n. So initially the temperature is at 0. I'm going to copy the solution and simply paste it into my summation formula set of a function t of t. I'm going to define a function u, and I'm going to plot it. So here I plot both the solution and the heating function. Initially the temperature is at 0, so the temperature is uniformly 0. Then the temperature started to rise. And then once the heating is turned off, the temperatures quickly drop to 0. Things happen very quickly. So in order for me to see what's going on, what I'm going to do is I'm going to change the coefficient kappa from 1/2 to something like 1/16, just so that I can see the effects of cooling down on a much slower time scale. So when the heating is initially applied, I can see that the middle section of my rod heats up very quickly. And due to much slower heat transfer right now, with a smaller constant kappa, I can see that the tail ends of this rod are not up, and they're much cooler than the middle section. Then at some point, things kind of level off, and the temperature becomes almost linear up to this section where the heat is applied. And then the heat is abruptly turned off and everything cools down. Let's watch it again. We can see how the temperature quickly rises in the middle and the end's temperature at 0. Heat has not reached them yet. And then the heat reaches the ends, and the temperatures rise almost uniformly on the tail ends, and there's this big pump in the middle where the heat is actually applied. And then once the source of the heat is turned off, everything cools down quickly. We can apply this method to the wave equation with very little changes. The only thing that will change is the differential equation right here. Instead of having the first derivative in terms of time, the wave equation requires the second derivative on this side of the equation. And so the term t prime will only change to t double prime. And instead of the first order equation, we will have a second order equation with slightly different solutions. And instead of single initial condition, we'll need two initial conditions for both u of x0 and ut of x0. But the idea is the same and the algorithm will stay the same. So this is how you solve non-homogeneous heat equation. And by virtue of expanding these ideas onto the wave equation, you can also solve the wave equation. The Laplace equation is a lot different and a lot more complicated, so we'll skip the discussion of the non-homogeneous Laplace equations. And if you're interested in solving non-homogeneous Laplace equations, I'll be more than happy to provide you with the resources and the reading material on this topic. For now, this is it. I hope you enjoyed the lecture, and I'll see you in our next video.